Infinity. Something we can think about rigorously yet never encounter and experience. In mathematics, infinity often functions potentially rather than actually. We imagine continuing a process indefinitely, and from this endless possibility extract precise conclusions. But how can reasoning about something that is never completed produce definite results? How can an infinite process settle into a definite value? Convergence is the principle that makes infinity mathematically manageable. It tells us that although we may add infinitely many terms, take infinitely many steps, or refine a process without end, the result need not spiral out of control. Instead, the sequence of approximations can quietly close in on a single, fixed quantity. Mathematics often asks us to perform operations that never truly finish, yet still promises that, in the limit, something perfectly definite emerges.
I think this theme of taming infinity is definitely one of the most interesting aspects of mathematics.
In the theory of series, infinitely many terms may be added together, yet the process remains intelligible because we study the behavior of the partial sums. If these sums approach a fixed value, the infinite addition is said to converge. Likewise, in integration, the area under a curve is defined through an indefinitely refined process of approximation, sums of ever thinner rectangles whose total approaches a single limiting quantity. In both contexts, convergence transforms what appears to be an unending procedure into a determinate object of analysis. The infinite steps are never completed, yet their cumulative behavior stabilizes, allowing mathematicians to reason about infinite processes as though they culminate in a precise result. Through convergence, infinity becomes not an obstacle, but a structured path toward exactness.
A series diverges or converges if your series is given by a clean formula where you could integrate. So in convergence of series, you can use what's called integral test, which is usually taught in calculus courses, which is that if you have an infinite series of numbers which arise as values of a given function at the integers, then you can basically compare that infinite series with saying that it is basically not too far off from being the integral of that function itself.
The convergence of series and the convergence of integrals are closely related because both concepts analyze the limiting behavior of cumulative quantities. A series accumulates discrete contributions term by term, while an integral accumulates continuously across an interval. In both cases, convergence occurs when the sequence of approximations, partial sums in the case of a series, or increasingly refined area approximations in the case of an integral, approaches a finite limit. When a function generating the terms of a series behaves smoothly and predictably, the discrete accumulation of its values mirrors the continuous accumulation represented by the integral of that function. Thus, the study of convergence in each framework becomes structurally parallel. Both ask whether an indefinitely extending process stabilizes toward a determinate quantity. This structural similarity permits the integral test for convergence. If the terms of a series are given by a function that is positive, continuous, and decreasing, then the sum of the series can be compared directly to the area under the corresponding curve. Each term of the series corresponds to the area of a rectangle, while the integral measures the area beneath the curve itself. Because the rectangles either slightly overestimate or underestimate the area in a systematic way, the long-run behavior of the sum and the integral must align. If the integral converges to a finite value, the series must also converge, and if the integral diverges, so too must the series. The relationship between discrete summation and continuous accumulation, therefore provides a bridge through which the convergence of an infinite sum can be determined by analyzing an integral.
So this tells us, you see, like, then now because all the terms are positive, so this Sn is like monotone. So we can compare. So if this integral converges when n goes to infinity, then this sequence, then this infinite series converges.
One thing that you have to make sure is that the difference between series and integral is not too off. So for example, you would want your function to be decreasing. Like if your function is like just like randomly like bouncing off and on, then the difference between series and integral might accumulate to an infinite amount, where as to this comparison between integral and series becomes meaningless. So one way that is usually, I guess, ensured in the standard calculus course is that this function is decreasing over time.
So the integral test works well if, first of all, so your an is of this form.
Okay.
And secondly, you need to be able to tell if this improper integral converges.
The relationship between integrals and series also points toward a broader strategy for understanding convergence. Rather than attempting to compute the value of an infinite sum directly, we can often determine its behavior by comparing it to another infinite process whose behavior is already known. This idea motivates the comparison test for convergence. The comparison test states that if your series, a sub n, is less than another series, b sub n, for all sufficiently large n, then the behavior of the a sub n series can be inferred from the b sub n series. Specifically, if the greater b sub n series converges, then the lesser a sub n series must also converge. Conversely, if the lesser a sub n series diverges, then the greater b sub n series must diverge as well. The theoretical rationale behind the comparison test rests on the cumulative nature of infinite sums. Because a series is defined through the growth of its partial sums, bounding the individual terms of one series by those of another effectively bounds the growth of their totals. If each term of one series is no larger than the corresponding term of a series whose infinite sum remains finite, then the accumulating sum cannot exceed that finite bound in the limit. In this way, convergence becomes a relational property. Rather than evaluating an infinite process in isolation, we situate it within a network of inequalities that constrain how large its cumulative value can become. Seen in this light, the comparison test extends the conceptual lesson already suggested by the integral test. Both methods rely on placing an unfamiliar infinite process alongside a more tractable one, whether a continuous accumulation measured by an integral or another series with known behavior. Through such comparisons, the seemingly unwieldy character of infinity becomes manageable. Instead of calculating every step of an infinite process, we determine its fate by understanding how its growth relates to processes whose convergence or divergence is already established.
So if you have two series and they are both positive and one is bigger than the other,
Okay.
then if the larger one converges, then yeah, the smaller one converges.
Okay.
So if the smaller one diverges, yeah, this is, and then the larger one diverges. This is
basically if it looks like if your series looks like you're something that you're more familiar with, plus some wiggle terms that you know that they are kind of not too big, then you can use comparison tests successfully.
so in order to apply this, you need to either know this is true or know this is true.
Okay.
And then so then there's some so this series, so we just see that when p is equal to 1, this diverges. So this converges if actually p is greater than 1. And to prove this, actually, this you compare it with so you know that this converges if p is greater than 1. Suppose that you know this. So we see that this is less than 1 over n squared.
Okay.
So, and then we know that from here, we know that so this converges. So we find some bigger infinite series, which is a benchmark.
Okay.
So then we can conclude that yes, right. So because this is a geometric series,
Okay.
so this is also some other benchmark series. If you have some series, which you can relate to the benchmark series, then you can apply the comparison test.
The integral test and the comparison test both show that infinity is not confronted directly. Instead, it is approached indirectly through limits, bounds, and relationships between processes. We never perform infinitely many additions, nor do we complete infinitely many refinements of an integral. Yet, mathematics proceeds as if the outcome of such endless procedures were perfectly well defined. This raises an unavoidable question lurking behind the technical machinery of convergence. What is infinity really? Infinity seems to resist the ordinary structure of things. It is not an object we encounter, nor a magnitude we can measure. Rather, it emerges when a process refuses to terminate, when counting, dividing, or refining can continue without bound. Mathematics gives this boundlessness discipline through the language of limits and convergence, allowing infinite processes to yield finite and exact results. But the philosophical tension remains. Are these infinite processes merely potential, always capable of continuing but never complete, or do they somehow exist as fully realized totalities within the abstract universe mathematics describes? The unease arises because convergence suggests something almost paradoxical. An endless sequence of steps can nevertheless stabilize into a single value. The infinite, which seems by nature uncontainable, appears to culminate in something definite. In this sense, infinity sits at the edge of mathematical thought like a dark horizon, never reached, yet constantly shaping the landscape. Convergence does not eliminate infinity. It reveals a strange order within it, hinting that even the boundless may obey hidden structures that mathematics may or may not ever fully uncover.
got a series staring back at you. Terms go on forever through and through. If the terms behave like a function should, there's a calculus trick that works real good. First, make sure the rules all check out right. Positive terms and decreasing in sight. Continuous too, that's the key to see. Then turn that series to an integral. Positive, continuous, decreasing too. Then the integral test will work for you. If the integral ends, the series ends. If the integral blows up, divergence wins. Integral finite, series behaves. Integral infinite, divergence wins. Sometimes the terms look tough to tame, but you know a series with a famous name. Find a bigger one or a smaller friend, then let the comparison bring the end. If yours is smaller than a convergent crew, then convergence passes down to you. But if yours is bigger than a divergent line, then divergence spreads down the vine. Smaller than convergent, you converge to. Bigger than divergent, divergence for you. That's the inequality, that's the quest. That's how you win the comparison test. If the terms look similar but not the same, direct comparison's a guessing game. Take the limit of their ratio instead. Let infinity tell you what lies ahead. Compute the limit of beyond over bn. Let it go to infinity. See what's done. If the limit's positive and finite, you'll see both converge or diverge together perfectly. Limit of ratios, let them go high. Positive, finite, they live or die. Same behavior, that's the key. Limit comparison tells the destiny.